out, that actually stimulates more growth of those cattails. Kind of like cutting a lawn. When you cut it, things start to grow faster. And so we're all using local cattails. To me, the question is, should we be putting other species in here besides cattails? Yeah, and I absolutely think we should. There are some rushes. I'll point some of these out when we walk to the bioretention unit. There are rushes, which are and other aquatic members of the grass group, reeds, we call them reeds and so forth. And to diversify the species that are in that system, this bioswale would be great. Now, if you look at the end of the bioswale, we'll get a closer look, Pete, but from up here it shows so well. You can see a pool, and that pool is the bottom of the whole system. And the idea is to trap all the water that has moved in that pool and let it stay there and provide a valuable ecological habitat. We'll talk a lot about wetlands in this class. So now we have a wetlands, if you will, or a small pool, right outside the window of the biology lab. So it's great. But we need to avoid mosquitoes. Anytime you have still water, then you have a mosquito risk. What other options? Yeah, you can try to ensure that there's a continuous flow. That's another way. What else? Larvicide. That'd be a special kind of chemical, particularly for the larvae, the non-emergent skeeters. What does it mean if I say you're going to use biological control?
You're going to introduce species that will feed on mosquitoes.
Yeah, that's right. You introduce species that will eat the mosquitoes. And there's actually a fish called Gambusia. That's the scientific name of the mosquito fish. And they'll eat it. So will frogs, plenty of different types of baby frogs, pollywogs or tadpoles. So you just have to have a vigorous environment. Now this whole bioswale system is struggling a little bit with growth, and here's why. Because you can see the water's coming off this roof, right? There's where it's coming out, and we know that it's going through a pipe and coming right out in the bioswale. Plus you have a bunch of concrete. And the concrete is eroding or slowly, before it sets, releasing some of the material, the lime, the concrete. What's that going to do to the pH of the water? High pH water. It's probably quite basic. And the cattails don't like it. I mean, I can tell, because I know a healthy cattail. We'll see some down there. And these guys are struggling because the pH is so high. But one of the interesting things about plants is that plants modify the environment, given time, to make the environment better for themselves, the plants themselves. So these cattails, although they're struggling now, they are surviving and they're producing organic matter, and the organic matter is gradually sloughing off. The plant's always growing and it's always shedding material. And the organic matter is not high pH. The organic matter is neutral, or maybe even a little bit acidic, humic acid. And so it's gradually modifying the environment to make the environment better for the plants. And you see that in any system. You can go out to an area and absolutely clear the soil and expose it, and gradually, it take generations, or it may happen faster. Plants will move in, they'll modify that raw, bare, inhospitable soil into to a better soil for which more and more a richer and more diverse plant community will grow. Does anybody know what that's called? The way plants actually change the environment and bigger and more complex plant communities move in? Ecological succession. The reforestation will be an application of it. So ecological succession, the series of stages starting from an unvegetated area or condition up to what's called a climax, which is a rich, diverse, and productive system, because the invader plants make the soil better for the second tier of plants, which make the soil better for the third tier of plants, and they continually improve in this series succession the condition of the soil. Okay, so we're going to go and we get a good view of the whole system, and then we'll head to the next stop. Any questions?
Earlier that Brad just talked to me about the erosion.
Yep.
Maybe he said maybe the solution would be by creating another.
Absolutely. That was one of the first things that I noticed when I came back, because I had helped design this system while I was at the late spring, and then I left for the United States, and then I came back and was so curious, a little disheartened by that erosion there. But then I noticed that this whole other line had formed, and it's interesting that it's literally parallel to the one that we engineer. So nature did its own engineering. And that's one of the most important concepts in design. It used to be that humans did all their designing from within. They said, all right, I am going to design for beauty and functionality, and the capacity to achieve those goals is in my own education and my own head. It was about 20 years ago when all of a sudden there was, again, a paradigm shift. That's what we learn about in this class, is how people got smarter. There was this paradigm shift called design with nature. Instead of designing a system that's from our own heads and educations and just imposing it on a natural system, we look at nature. Nature talks to us. And then we design to harvest those attributes or emulate nature. One of my favorite stories related to that has to do with water. Y'all know I'm a bird watcher, right? This is related to bird. Okay, so we're going to go to when Japan first invented the bullet trains. And they had these bullet trains that were going super fast, 200, 250 miles an hour. And when they would go into a tunnel, well, it was particularly they go into a tunnel, and then when they would come out of the tunnel, there'd be this huge boom. And the people who lived near there were complaining because the glasses on their shelves would rattle. Every once in a while, a window would break, and so forth, because the change in media from the air of the tunnel to a slightly different density of air outside the tunnel generated this sort of equivalent of a sonic boom. So the engineers went to work. They did calculations, same kind of things that goes into designing an airplane. And no matter what different types of nose cones they put on those trains, they still had a boom or vibrations that made the people around it miserable. Then some biologists said, you know what? A kingfisher, which is a bird with a long pointy bill, the last thing it wants to do when it enters the water is scare off the fish. So an engineer went and he measured the exact proportions of a kingfisher bill. They designed a nose cone for the train that was exactly shaped like that, put that on the train, and the first time the train came out of the tunnel, it was dead quiet. No vibrations at all. And so, how did it get that way? Why is a kingfisher's bill so perfectly designed to not create the vibrations when it hits the water? It's streamlined so as not to scare the fish that it wants to eat. And that's, for those of us who go with the evolutionary paradigm, That's how evolution works, is that at some point there were kingfishers out there whose bills were not just right, and those kingfishers couldn't get enough to eat. Whereas another kingfisher that may have had a slight mutation, a slight change in its bill configuration, and that kingfisher found it so much easier to catch fish that it survived and was and reproduced, and the other kingfisher didn't. So when you take nature and millions of years of evolution, you're creating a system that is truly optimized. And engineers should appreciate that and not try to think that their education, their computer-aided design systems can replace that incredibly powerful force of optimization driven by evolution or intelligent design, whatever you want to believe. Okay? Great. Flowers, and all that stuff. By these little lateral rhizomes or like stems that go under the soil, and then they come up somewhere else. So pretty soon this will fill in. Plus you'll get lots of other species living here. Plus we'll get animals, frogs, and now the day will even come that you see like a couple of little birds, wading birds, and fishes in here. And they'll all start to evolve into a more and more complex aquatic ecosystem. And right now it's serving this great utility of holding water back before the water leaves here where it can cause flooding and erosion. Did one of you have a question?
I think the base thing is not base is probably just soil and loose rock.
Yeah, and actually I'm a little surprised and slightly disappointed that the water isn't infiltrating better. It makes me think that the whole thing is underlain by an impermeable clay pan. Because what would be better, in fact the way the system is designed to work, is the water would infiltrate and then say provide through the soil root water for that tree and all the trees around it. And it's the stone pitching and the lime that's being moved that's creating this undesirable impermeable pan. But it goes back to what I was saying. Give plants time to change the environment and they'll modify it in a good way. And these cattails will eventually send their roots deep enough, they'll churn up and loosen the soil, they'll increase its permeability, and then the system will become more of a natural system. It just needs time to make progress, diversify, undergo natural succession.
So,
Yeah.
what of dry season? Are we going to be having water?
Good question. Dry season, what's going to happen? Well, it could just dry up altogether. In other words, there would be no water source at all, in which case it'll dry up and these cattails will all become brown, like the brown-gray stems that you see. I know that there is fugitive water. That's what I call it. There's water in other areas of campus from things like leaking pipes, where they wash cars, other places where water streams continuously. You've probably noticed it by the cafeteria. So I'm working with the water guy, Dahiru, a little bit on bended knee, which means I'm asking him to do this, to move that water from that drainage way where it's all getting lost over to this one where it'll be used. And this is actually slightly downhill. So all he's going to have to do is he's going to have to put in a trench, put in a pipe, and all that water that would leave campus and be lost for value would come into here and make this landscape greener. It's a concept. The waste there could be wealth here. We just have to build a system to make that happen.
It's just gravity flow or something.
It could, yeah, it would use gravity. Either you can just lay the pipe so that it's going downhill the whole way. That's one way. The other is to siphon it. Do y'all know what a siphon is? A siphon is, yeah, but it's a pump that's run by gravity. So with this, I'll have to show you how a siphon works sometime. It's really cool. Where you have the intake here and the outlet there, and it may go uphill, but you can get the water to go uphill if you put a siphon on it, and then the water will draw itself. So if anybody ever asks you, for instance on an exam, does water flow uphill? You can say yes, in siphons. And that has to do with the tensile capacity of the water. It's kind of like it has a certain amount of adhesion, like a glue. So help me remember, in class we'll do a siphon sometime. Okay. It's also asserted that there is a purged aquifer, and I'm going to need to draw on the whiteboard what that is. That's just taking some groundwater in certain areas and releasing it. Look how vigorous this area is right here. And it's not just cattails. You can see those cattails are starting to reproduce. We got lots of different species of grasses. We've got what we call wheatgrass over there. These are pretty lush little habitats. And that's what we want to emulate on the library. There's one thing about this that makes it sort of unnatural and less effective, and that is that it's straight. If it's straight, then water tends to move and not spend as long in the system. That's why your guts, your intestines are coiled, because you want something to go over a long, curvy route where you have more time between the substance, the flowing substance, and the medium. So this would even be a better system if it had been made nice and curvy, so there's plenty of chance for the water to be used. Bigger, what would they be? Dinosaur tracks. Dinosaur tracks look just like that. Okay, so this is really just about the coolest student project I've been involved in. It was really great. Ibrahim was like one of the drivers behind it. Before we got here, this stream was kind of like you see there. It was a straight stream. There wasn't a lot of contact between the water and biology. And the reason that's probably, it smells bad here, right?
Real bad.
That's because this water is polluted. It's polluted from the sinks, the showers, the various byproducts, if you will, of water usage and, in cleaning and other dorm activities. Plus, it could be that this has a sanitary component too, meaning, or an unsanitary component, meaning that there is septic water rising from very shallow, poorly engineered septic tanks and releasing all this very obnoxious biology. I am sure that if you were to drink this water, you would get sick within 15 minutes and you'd be sick for a week. So, and we knew that the water that was leaving the campus that way was so much in violation of environmental standards that, in fact, in the United States, a university president, and I'm not exaggerating, would go to jail for such an egregious violation of the Clean Water Act. Well, we don't enforce that act here in this country yet, so it was incumbent on us, the Student Environmental Club, to try to purify the water. And we didn't have a lot of expensive equipment. We couldn't afford tanks and vessels and all the different types of treatment technologies we'll learn about later in this class. So we're letting the plants do the work. None of these cattails were here until we came. And then we put a bunch of gravel in, most of which now we had it in like a dam. You can see it there. And then, but it's gotten kind of flattened out. And then we put the roots of the cattails in the gravel, which made for a very excellent medium. The gravel slowed the water down a lot, and that's why when the cattails were there, and the water was going slowly through the gravel. We called it a bioretention unit. We're retaining it by making it go slowly through the gravel, and it's biologically being treated. So now, you know, we've had big storms. God knows how high the water gets. You can almost start to see kind of a mud line as to how high the water gets when we're having a big storm. So the gravel's been spread out, but the deed was done. The cattails are flourishing here. All the water that goes anywhere near the roots of the cattail are going through, and this is really far less persuasive than, yeah. Okay, so you see these roots right here? These are loaded with fungi and bacteria. We call it the rhizosphere, meaning the environment around the root. And the bacteria and fungi that live on this are, if you will, as the nutrients go by, we're talking about nitrates and phosphates and other things that create pollution. These bacteria are actually grabbing it, slowing it down and saying, wait, that's my food. I need to metabolize that. And they're stripping it of a lot of its pollution. And you can even have like heavy metals. I don't know that that's a big issue here, but in other environments, you can have heavy metals and other types of pollutants, lead, arsenic, and so forth, and they'll be trapped as well and incorporated into the tissue of the cattail. And this may look like it's a plant that just lives for a year or two, but cattails actually can be thought of as sort of one big plant that's going to last for a really long time, many years. And this part will come and go, but the roots underneath it, that's actually the enduring portion of the plant that can live for years, decades. And as Ibrahim was saying earlier, it sequesters carbon. It builds a very carbon-rich soil, and it's great for wildlife. You may have noticed all the little birds flying around and everything. So we took it from a relatively straight, fast-moving system without a biology that was particularly purposeful, and we've made it into something that's slower, more wandering, and with the champion of all species for cleaning contaminated water. Okay.
Sir, question.
Yeah.
So you said that's like the longest serving part of the plant, that's the root. So I'm saying, what, in the instance like the question he asked earlier, in season changes, when it's dry season, the topmost part of the cattail can dry off, but the root will still be very active.
It will, yes.
So when another rain comes, it could just sprung out again.
It might, at worst, I mean, if it's really dry, long, bad time for growth, it'll just go dormant, and then it will remain there, but sort of inactive, still be physically useful because it's got a lot of mud and everything that would absorb water if it were to start to rain. But as soon as it rains with any regularity, the whole root system will come to life again. And then you'll start getting whole bunches of little green sprouts to replace the ones that are dead, and the whole system will be fully vigorous. We planted, what would you say, Ibrahim, maybe 15, 20 plants?
Yeah, actually close to that.
And look at how it's continuous now. It's dozens. It's 100 plant. It reproduced that fast. Plus, we've made a very favorable environment. Those of you who are interested in biofuels, this is castor bean oil. This is a potential oil-bearing plant that you could use to make biodiesel out of. Okay. So I'm going to rinse my hands. And yet I'm also going to be very mindful that they have biological contamination, so I'm going to keep them away from my face. So we want to work our way out that way. Let me go first, or